A very good evening to all the attendees who have joined today at 7 p.m. for this special public lecture, which is being organized by the National Academy of Sciences India Delhi chapter and the MHRD-Institution Innovation Council, the Upadhyaya College, under the aegis of DBT Star College program. And I request Professor Ajoy Khatak, who's the chairperson of the NASI Delhi chapter, and also a NASI Meghnad Saha Distinguished Professor, to kindly proceed further with the special public lectures introduction.
Thank you, Dr. Saxena, Dr. Manoj Saxena. I'm indeed very happy to be present to listen to this talk by Professor William D. Phillips. We have been looking forward to this talk, and we are really very, very grateful to him for agreeing to give this talk. And as Dr. Manoj Saxena mentioned, this is part of the activities of the Deen Dayal Upadhyaya College and also the National Academy of Sciences India, which is abbreviated as NASI, whose headquarters are in Prayagraj, which was known to be Allahabad earlier. So for Dr. Phillips, this is New Delhi, this is the map of India, and Allahabad or Prayagraj is on the bank of river Ganges in the state of Uttar Pradesh. It's about 400 kilometers from here. The Academy has 23 chapters in different parts of India, and Delhi is just one of them. The founder of this chapter was, one of the founders was Professor Meghnad Saha, and he was also the first president of the Academy. So this year we are celebrating 90 years of this Academy, and he was born today. So this is a very auspicious day for the Academy. Today is Professor Meghnad Saha's 127th birthday. Sorry. I must mention that he was a great astrophysicist, apart from creating this academy. And Sam Keen wrote an article, A Forgotten Star, a discovery by Indian scientist and statesman Meghnad Saha revealed the, Meghnad Saha revealed the nature of stars. So he was a great astrophysicist, and he was nominated for the Nobel Prize 6 times, but unfortunately he didn't get one. So it's my great pleasure and privilege to introduce Dr. William D. Phillips. He did his doctoral research with Professor Dan Kleppner at the Massachusetts Institute of Technology in Boston. The work concerned the magnetic moment of the proton in water. This is what I found in Wikipedia, but there must be other works also with which he must have been associated. He later did some work with Bose-Einstein condensates. Later, Dr. Phillips joined NIST, the National Institute of Standards and Technology at Gaithersburg, and there, along with his colleagues, he demonstrated the first atomic fountain clock. Such clocks, as realized in other laboratories, have become the primary time standards for world timekeeping. In 1997, as all of you would know, he won the Nobel Prize in Physics together with Cohen Tanuji and Stephen Chu for his contributions to laser cooling, a technique to slow the movement of gaseous atoms in order to better study them. At that time, he was working at the NIST. And the photograph on the right shows Professor Phillips receiving the Nobel Prize. Dr. Phillips is also a professor of physics, which is part of the University of Maryland College of Computer, Mathematical and Natural Sciences at University of Maryland at College Park. I thought I should mention this. Dr. Phillips is one of the 20 American recipients of the Nobel Prize in Physics to sign a letter addressed to President Bush in May 2008, urging for additional emergency funding for the Department of Energy's Office of Science, the National Science Foundation, and the National Institute of Standards and Technology. He was also one of the 35 Nobel laureates who signed a letter urging President Obama to provide a stable $15 billion per year support for clean energy research, technology, and demonstration. Why I have shown this particularly is because of the fact that I personally believe that we should also have much greater support from the government for fundamental research in our country. And so you are a role model for us. He is recipient of numerous awards: the Gold Medal of the U.S. Department of Commerce, the Michelson Medal of the Franklin Institute, the Schawlow Prize of the American Physical Society, Service to America Medal, etc., etc., etc. So with great pleasure, with tremendous pleasure, I request Dr. William Phillips to deliver his lecture on a new measure, the reforms of the international system of units. Professor William Phillips.
Thank you very much for that kind introduction. So now I'm going to try. I think you have to
Yeah.
stop sharing your screen so
Yes,
that I can start
yes.
sharing mine. Okay.
Yeah, please go ahead, sir.
Oh. Okay. Now let's go to full screen. Okay, so now do you see the full screen?
Yes, we do.
Excellent. Thank you very much. Okay, so as you've heard, I'm from the National Institute of Standards and Technology. This is the US equivalent of your National Physical Laboratory. I'm also part of the University of Maryland, and those two institutes together have joined to form the Joint Quantum Institute, which I'm part of, and I'm also part of the NIST Laser Cooling and Trapping Group. The group leader is Gretchen Campbell, and the other group members are Paulette, Trey Porto, Ian Spielman, and Ida Tietzinger. And we do laser cooling and trapping, as the name implies. And let me just make one clarification from the introduction. While we've done a lot of things having to do with laser cooling and trapping, the first atomic fountain clock, which I did work on, was done in Paris in the group of Claude Cohen-Tanucci, and that work was led by Christophe Salomon and many other colleagues. So I just wanted to make sure that I didn't take credit for something that was done in Paris. Okay, so let's talk about metrology. As I'm sure many of you know, the 20th of May is World Metrology Day, and on the 20th of May 2019, we experienced the greatest revolution in measurement since the French Revolution. And the nature of that revolution was to change the international system of units, the international metric system, in a fundamental way. And the way in which it has been changed is that all of the base units of the SI, of the kilogram, the meter, the second, the ampere, the Kelvin, the mole, and the candela, all of these base units are now defined by fixing the values of constants of nature. Now, to understand how it's possible that we can define these units, these basic units, by fixing the values of fundamental constants, and with apologies to the great late Stephen Hawking, I would like to bring you a short history of length. And the reason is because length had already been defined by defining a constant of nature. So in ancient times, length was defined by the size of the human body. The cubit was the distance between the elbow and the fingertip. The yard was the distance between the center of the body, or the nose, and the end of the arm. The fathom was the wingspan of a person. And this was particularly convenient because you always had the standards of measurement with you. But it wasn't very consistent. If you were buying fabric from a fabric merchant, then you might be getting a less fabric than you would hope for if the fabric merchant was short. So people realized that we needed a better way of doing things. By the way, I just want to make sure everyone realizes that if you have questions, you should put them into the Q&A section, and we'll answer all the questions at the end of the talk. Okay, so one of the solutions to this problem was to use not just the body of whoever was making the measurement, but a particular body. For example, the body of the monarch, the pharaoh in ancient Egypt. And the royal Egyptian cubit was based on the size of the pharaoh's forearm. But people realized that while that might be consistent, it wasn't very convenient because you didn't always have the pharaoh around to perform the measurement. And so the ancient Egyptians created a primary cubit standard made out of granite. And you see a picture of at least part of it right here. And when they were doing work in the field, for example, building the pyramids, they used secondary standards, which were made out of wood. And it was a requirement that the workers would recalibrate their wooden secondary standards against the primary stone standard every month. And the penalty for not calibrating was death. So these people really took their metrology quite seriously. And the result was that the pyramids are incredibly accurate. The baselines of the pyramid on the four sides are consistent to a tiny fraction of 1%. They're square to 12 arc seconds. So they really did good metrology back then, based on a primary standard of length that was an artifact made out of granite. That same, I'm sorry about the telephone ringing. It's perhaps a standard part of video conferences these days that there are interruptions of this sort. Anyway, similar artifacts were often used throughout Europe, varying from town to town. And the way it worked was they would take the standard of length and they would cement it into a stone wall, for example, in the town square. And here is an example of the city of Regensburg in Germany. And you can see that the fathom, which is indicated here, is quite a long fathom. So this would be a good place to buy fabric. But this standard was different from the region of surrounding Bavaria. And so this was a common problem throughout the world, that standards were not consistent. And then came the French Revolution with, among many other things, a philosophy that there should be consistent standards and that those standards should be available to everyone. And so in that spirit, they decided to define a new standard of length, which they called the meter, which was supposed to be the measure of all things. And it was supposed to be 1/10,000,000th of the distance between the pole and the equator on a meridian that goes through Paris. And they sent out a team of surveyors to survey some section of this going from Dunkirk to Barcelona, and then extrapolating to the rest of the globe, measuring in the old units so as to see what the conversion was between the old units and the new units. And the dream of that time of making this kind of redefinition of the standard of length was that they would have standards that were good for all times, for all people. And this medal was cast to commemorate this idea. And you'll notice they have an angel with dividers symbolically measuring the earth. But they actually sent surveyors out to measure the earth. But the problem was that definition of a meter based on the size of the earth was consistent and available, but not easily available, because to check it, you had to send out a team of surveyors, and it took years. So what they did was they took the results that these surveyors had gotten, and they made a metal bar. So this was just like the approach that was used in ancient Egypt. They made a metal bar out of platinum, and that became what was known as the meter of the archives, the standard of length for the country of France in revolutionary times, 1799. In 1875, there was an international treaty in which a number of countries of the world agreed to adopt the meter as the standard of length, and the kilogram as the standard of mass. And shortly after that that treaty was signed in 1875, a new meter was made, and the meter was defined as the distance between two scratches on this platinum iridium bar. And it was made to be as close as possible to the size of the old meter of the archives. But almost as soon as this new meter had come into effect, people realized that they had a much better way of measuring length. People in the 19th century had discovered that light was a wave and that they could do interferometry. And here I show a schematic of a particular kind of interferometer. This one is a Michelson interferometer. And if you move this mirror, the interference pattern shown here or here changes. If you move this mirror just 1/4 of a wavelength of light, which is to say perhaps 100 or 200 nanometers, then this spot in the center will change from being dark to light. Now, a quarter of a wavelength of light is much smaller than the size of the scratch on the meter bar. And so it soon became clear that the definition of the meter was not as good as the techniques that had been developed for measuring length. But it took until the year 1960 for people to change the definition. So between the time that the new meter bar was established and 1960, people still used the wavelength of light as a kind of de facto standard, not the real metric definition of the meter, but a de facto standard. And not until 1960 was the definition of the meter changed to be a certain number of wavelengths of light from a lamp of krypton. Now, 1960 was the year the laser was invented. And very soon, it was clear to people using krypton lamps as standards of length that that purity of the light coming from that krypton lamp was insufficient for the accuracy that people were making with laser light, because soon people made lasers with extremely pure light output. And so the wavelength of the light coming from these lasers was much more stable, much easier to measure than the light coming from the lamp. And so people started to use laser light as an unofficial de facto standard. And that continued for a number of years until people decided we need to redefine, again, we need to redefine the meter. Now, the most obvious thing to do would have been to redefine the meter in terms of the wavelength of some laser. A laser stabilized to a particular absorption line in molecular iodine was the most popular standard of the time. That would have been the obvious choice. But fortunately, people did not make the obvious choice. They made a brilliant choice, a beautiful choice. They defined the speed of light. So whereas the old definition of the meter was a certain number of wavelengths of the light coming from a krypton lamp, the new definition of the meter was the length of path traveled by light in vacuum during a certain time interval, and that time interval is 1 over the speed of light in meters per second. Why is this such a beautiful definition? Because if you can measure the frequency of light, and people in 1983 had learned how to measure the frequency of light, and if you define the speed of light, then that means you know what the wavelength is, because this relationship, the wavelength times the frequency is equal to the speed of light, is true for all light regardless of its frequency. And so once you know how to measure the frequency of the light, once you define the speed of light by this definition of the meter, you have a ruler for any frequency of light. And so if someone makes a better laser, so the light is more pure, if someone develops a better technique for measuring the frequency of light, the old definition, that is this definition, is still perfect. And you can still use it to make a better meter. And so people did make better lasers. People did develop better ways of measuring the frequency of light. And this definition still is good and continues to be good. And I see no reason why one should ever need to change this definition of the meter. And this is what I call a beautiful definition, a brilliant definition. And now this is what we want to do for the kilogram, and for that matter, the ampere, the Kelvin, and the mole. And that's what was done on the 20th of May of 2019. We brought that kind of beautiful definition to the kilogram and these other units. Why did we have to do that, and how was it done? And so in order to explain that, I'm going to give you a light history of mass. So in ancient times, masses were artifact standards, pieces of stone that had been polished. This is a set of such masses from ancient Babylonia. But in the time of the French Revolution, people thought we should have a more universal definition of mass, and that definition was based on the new definition of the meter. It was a kilogram, the new definition of mass, the new unit of mass, was the mass of 1 liter, which is 1 cubic decimeter of water. So that became the new mass standard. All you had to do was measure out 1 liter of water, and you had a kilogram. The trouble was, it wasn't very easy to measure out 1 liter of water. And so a familiar story, they made an artifact. They made a cylinder. You see me holding that exact cylinder that was made and deposited in 1799. I'm holding it right there. Made out of platinum, equal to as close as they could make it to the mass of a liter of water. And this artifact became the mass standard. And in 1875, after the convention of the meter, they made a new kilogram, and you see it here under these bell jars. And this was the standard of mass for the entire world up until the redefinition on the 20th of May, 2019. This is the Indian national prototype of the kilogram. It looks pretty much the same. It's a little tiny cylinder. And the thing is, this is the last artifact. We've changed the definition of length already, gotten rid of that artifact. But now we are in the 21st century, and we are using an artifact that was made in the 19th century that was based on an artifact that was made in the 18th century. It's such a scandal that we should be doing such things that an American newspaper comic made fun of it. Is there a question? Okay, so I think we're running a little bit low on time, so I'm not going to show you this cartoon, but you can ask about it later at the end of the talk, and I'll be happy to show it to you. But the point is, one of the things that is so terrible about this scandalous situation is that it appears that the mass of the international prototype is changing. This shows a plot of the mass of a number of different kilograms that various countries, like India and the United States, have relative to the kilogram. And you notice they almost all seem to be going in the same direction. Well, that makes you think that maybe it's the kilogram itself that is changing. But by definition, it cannot change. By definition, it is always a kilogram. If it gains a little bit of weight, if somebody leaves a fingerprint on the international prototype of the kilogram, everyone else in the world loses weight. We cannot have that situation. And so we have to fix it, and we want to fix it using this beautiful approach where we define a fundamental constant of nature. When we defined the meter, we defined the speed of light. What are we going to use to define the kilogram? Well, in order to explain that, let's recall what is certainly the most famous equation in all of history, that E equals mc squared. E is the energy of an object at rest. M is what we call its rest mass. And C, of course, is the velocity of light. Now, there's another equation that's not quite as famous, that the energy of a photon, a particle of light, is equal to Planck's constant times the frequency of the light. Now, if we join these two equations together and solve for the mass, we find that the mass is equal to Planck's constant times the frequency divided by the speed of light. What does this mean? It means that if I have an object and it emits a photon of frequency f, then its mass is given by that frequency times Planck's constant divided by the speed of light squared. Now, we've already defined the speed of light in 1983, so you see that if we define Planck's constant, then we have a definition of mass. We know what the change in mass is of some object if it emits a photon. Now, we're not actually going to do it that way. We're not going to be weighing photons. We can, in fact, weigh photons, but not well enough. But this guy, Brian Kibble, of the NPL in the UK, developed a way that we now call the Kibble balance or the Watt balance for doing this. And this movie explains how it works. So first, let's remember how we weigh things traditionally. Let's say we have an unknown mass on the right-hand side of this balance. The way we determine what its mass is that we add standard masses to it on the other side of the balance until the balance balances. And this is the traditional way of weighing things. Now, I'd like you to imagine another possible way of weighing things. Instead of using a standard mass, we have a coil of wire and a permanent magnet. And as you know, if you have a current flowing in the presence of a magnetic field, there will be a force exerted on that current because of the electromagnetic force. We sometimes refer to this as the Lorentz force. But in any case, there will be a force. And if we knew exactly what the magnetic field was, and if we knew exactly where the current was flowing in these wires, then we could use this as an alternative way of determining this unknown mass by balancing the gravitational force against the electromagnetic force. But we don't know those things. We don't and never can measure the magnetic field well enough. And we never know where the wires are well enough, even if we know what the current is. But Kibble came up with a brilliant idea. His idea was take that coil of wire, take the leads of that coil and attach them to a voltmeter. Now move the coil in the field of that magnet, and that coil will generate a voltage, which you can see here shown schematically. And the faster the coil goes, the more the voltage will be. So you measure the velocity. We call this the velocity mode. You measure the voltage, and that gives you the information that you need about the geometry of the coil and about the strength of the magnetic field. Now, the other part of the measurement is that you weigh the coil, that is, you measure its force against some mass, and that's what we call the weighing mode. The combination of these two different parts of the measurement, the weighing mode and the velocity mode, allows you to do everything that you want. So let's go to, here's how it works. We measure the mass in the weighing mode. We multiply it by the acceleration of gravity, which we can measure locally. That gives us the force from the weighing mode. We multiply that force times the velocity from the velocity mode, and that has to equal the current from the weighing mode times the voltage that you measure in the velocity mode. And why are they equal? Because mechanical power has to be equal to electrical power. Force times velocity is mechanical power. Current times voltage is electrical power. And so we solve for the mass, and we find that the mass is equal to the current from the weighing mode times the voltage from the velocity mode divided by the acceleration of gravity and the velocity from the velocity mode. Now, a new way of getting mass. But remember, I promised you that we were going to redefine mass by using Planck's constant. So how does that happen? And it happens because of the way in which we do the electrical measurements in modern times, the way in which we measure current and voltage. The voltage is measured using the Josephson effect, which I'm not going to explain right now, but we can talk about it later if you want. And so the voltage that you measure is proportional to H over 2E. And the current, by the time we measure current using the quantum Hall effect, which gives us a quantum resistance, the current is proportional to E. And when you multiply H over 2E times E, you find that the mass is proportional to Planck's constant, as I promised. So this is just a picture of Brian Josephson, who gave us the Josephson effect, and Klaus von Klitzing, who gave us the quantum Hall effect. The Josephson effect in hertz per volt, so we measure frequency and we can get voltage, and the von Klitzing constant in H over 2 over E squared, which is in ohms, giving us resistance, and balances like this, the one that I showed in the movie, can now realize the kilogram. And realize is a technical term that we use for bringing the definition of the kilogram into reality. So creating a real kilogram out of the definition is what we mean by realizing the kilogram. It can be done with an accuracy of about a part in 10 to the 8th, which is better than the changes that have been happening to the kilogram due to whatever dirt gets on it that we don't understand yet. Here is a team at the National Institute of Standards and Technology who have done the most recent realization. These people, like the ancient Egyptians, are really serious about their metrology. They have tattooed the new values of Planck's constant and the other defining constants of the reformed SI onto their arms just to show how serious they are about their metrology. And this new value of Planck's constant comes from the measurement they made using the Kibble balance. Now, there's another way of doing it. You don't have to use a Kibble balance once you've defined Planck's constant. There's another method involving a nearly perfect silicon sphere, which has been realized at the Physikalische Technische Bundesanstalt, the Standards Laboratory of Germany. And I don't have time to tell you about that right now, but I'd be happy to talk about it in the question period. So now there are laboratories all over the world using Kibble balances or using silicon spheres, including in India. And here is a picture of the NPL India watt balance. And it's wonderful because you can see the parts of it. Here is one of the permanent magnets. There's the current carrying coil that you saw in the movie. Down here is a laser sensor that can be used to measure the velocity. All these things are the things you need to make this Kibble balance work. Here we have a voltage standard that's used to determine the current. So all these pieces are beautifully visible in this picture. Now, there's a final part to the story. The ampere has been redefined. It used to be, before May of 2019, that the ampere is the current which in two infinitely long straight wires, 1 meter apart in vacuum, would produce a force of 2 times 10 to the minus 7 newtons per meter. The new definition is gotten by defining the charge of the electron. So the ampere is simply a certain number of electrons per second. Now, we don't count electrons. Well, we could, but we can't do it well enough. But once you've defined both E and H, then that means that 2E over H and H over E squared, the Josephson constant and the von Klitzing constant, are exactly defined. And that means that we can do electrical measurements using these defined values. Now, here's something that very few people know. Since 1990, the legal electrical units were defined by choosing fixed values for 2E over H and H over E squared. These were not the SI values, not the International System of Units, but just a convenient legal definition, and people measured current and voltage and resistance in these legal units, which were not SI units, but were the ones that were used in every ordinary commerce and the way in which all voltmeters were calibrated. So in fact, we had two different systems of electrical units, one based on 2E over H and H over E squared, that were the legal ones, and another one based on that old definition of the ampere having to do with forces between wires. That was the scientific definition. Now, because of the fact that we've defined H and we've defined E squared, we now have the legal and the SI definitions are identical. That's a wonderful result of this redefinition in the SI. And this is a cartoon just to illustrate how this is done. You have a resistor that's calibrated against the von Klitzing effect. You have a voltmeter that's calibrated against the voltage effect, against the Josephson effect. And so that gives you a voltage in terms of H over 2E, a resistance in terms of H over E squared, and the current, which is voltage divided by resistance. You see, if we take the H over 2E and we divide that by H over E squared, it gives you a current proportional to E, just as I promised you earlier. So two more units have had their values changed. The mole used to be the amount of substance that had the number of entities equal to the number of carbon-12 atoms in 12 grams of carbon-12. But now it's just a number, which means we have defined Avogadro's number. The Kelvin used to be 1 over 273.16 of the triple point of water. But now we've defined the Boltzmann constant. And so the Kelvin is simply defined in terms of the energy of the atomic constituents, because we know that in thermal equilibrium, we have 1/2 kT of energy in every degree of freedom. So once we've defined K, if we can measure the energy of those things, we've got the temperature. So this is the reform of the SI. The French Revolution gave us the metric system. This new revolution has given us a final realization of this dream of revolutionary spirit that would give us uniform constants. And now we have this additional feature that we don't have a double standard for electrical measurements. The SI and the legal units are the same. And so now all of the fundamental units of the SI are defined by defining constants of nature, the kilogram from Planck's constant, the meter from the speed of light, the second from the hyperfine separation of cesium, which we'll talk about in a moment, the ampere from the electron, the Kelvin from the Planck constant, and the mole from Avogadro's constant. And so now all of these constants are defined. You can keep this card in your wallet, and you know the entire SI. So have we finally realized the dream of something that's good for all times and for all people? Well, these people certainly thought so. I want to play this movie that was played at the redefinition, the international decision.
It took more than 140 years.
Groundbreaking science.
And the agreement from the world's scientific community. At times, it seemed
Impossible.
accurate.
Precise measurements.
Anytime.
Anywhere. But
We did it. Ce l'abbiamo fatta. Wir haben es geschafft. Lo logramos.
Lei sia buoni. 我们做到了。
Wyzwolona Europa. Proud dai.
Het is ons gelukt.
Fantasami.
Die jongen weg.
America.
Do kázali jsme to.
Sewena.
Congratulations. Kamila. Felicitaciones.
Bazalto. Congratulazioni.
Shate Lavorisha. Sama sukses. Parabéns. Ongera. Omedetou. Kamuguida. Konnichiwa. Mabruk.
Kapai. Congratulations.
Seeing that movie still is very emotional to me. 60 countries of the world, the signers of the International Treaty of the Meter, all agreed unanimously to redefine the SI in the way that we've described, something that is now good for all times and for all people. But it's not quite. And the reason is the definition of time itself. The current definition of time is based on the hyperfine frequency of cesium, a microwave frequency at about 9 gigahertz. This is the NIST atomic fountain, laser-cooled atoms. This is the NPL primary standard for cesium. But the point is that even though these primary standards are the very best thing that can be measured in the SI, they're good to a few parts in 10 to the 16, whereas we only measure mass to parts in 10 to the 8th. There are better ways of doing it. At NIST and elsewhere, people are developing optical frequency standards. So instead of at microwave frequencies, these are at optical frequencies, a few times 10 to the 14, and they're 100 times better than the cesium standard, but they don't represent an SI measurement of time because they aren't the SI definition. They've now become de facto standards, just like the same old story that we've seen. Even better, a single trapped ion has achieved accuracy better than 1 part in 10 to the 18. In India, a former colleague, an alumnus of NIST's laser cooling group, Upadhyaya, is doing the same kinds of measurement, a single trapped terbium ion. These are going to be the frequency standards of the future. There's going to be a redefinition of the definition of the meter, just as we had to redefine time from astronomical standards, length from artifacts, mass from artifacts. We're going to have to decide how to redefine the second. And the problem is that however we do it, it seems like on the horizon there will always be a better definition. There's no fundamental constant whose definition will satisfy the needs of frequency metrology. And so it seems like we've almost achieved the revolutionary ideal, except for time itself. Thanks very much. Now I'm happy to answer your questions.
There are about 20 odd questions. So would you like to see them, or shall I?
No, I think it's best if you just repeat them.
Okay, so I'll take up the first one. That's by Chirag Arora. And he asked that when we talk about measurements at the quantum scale, then the precision that we are concerned with is intrinsically limited by the well-known uncertainty principle. Do you think there is a way to indirectly or directly break this barrier and get a more precise measurement than that limited by the uncertainty principle?
Okay, well, that's an excellent question. It has so many features to it. I'm so happy that you've asked that. So first of all, let me say that that even though we have a quantum definition of these standards like voltage and resistance, using the quantum effects of the Josephson effect and the quantum Hall effect, the measurements are actually made on a macroscopic scale, so that we, in fact, for those measurements, are not in fact limited by the uncertainty principle. We're limited by much more mundane things like noise in our electrical measurements, thermal noise, even though these things are often done at cryogenic temperatures and we use cryogenic amplifiers. We're often limited by thermal noise or other kinds of technical difficulties. But it's still very, very important to think about the uncertainty principle, because as we get better and better at measurements, whether they're measurements of the fundamental standards of the SI or any other kinds of measurements, if we do well enough, then eventually we will get down to quantum noise, namely the uncertainty principle, as limiting our measurements. And there are any number of things where we are in fact limited by the uncertainty principle. One of the most famous examples, and one that illustrates the answer to the second part of your question, is LIGO and other gravity wave detectors. These detectors measure the position of a mirror so accurately and in a way that gets rid of other sources of noise that they are in fact limited by the uncertainty principle, by the quantum noise of the light that is used to measure the position of the mirror. And in order to improve on that quantum limit, they have done what is called squeezing. So what they do is they don't beat the uncertainty principle, but they, in a certain sense, cheat the uncertainty principle. Remember, the uncertainty principle says that you cannot measure both the position and the momentum of something at the same time to infinite precision. That if you have more precision on the position, you'll have less precision on the momentum. Well, what squeezing does is it accepts a larger uncertainty on something that you don't care about in order to get a better uncertainty, a smaller uncertainty on something you do care about. So in the case of LIGO, what you're looking at is the phase of light, because that's the thing that determines, that allows you to measure the position of a mirror. And the thing that is conjugate, what we say the other variable in the uncertainty principle, to phase is the number of photons. So what you can do is create a state of light where the phase is better known than would be the case for ordinary laser light, but the number of photons is less well known, or the other way around. And in this way, that these so-called squeeze states of light allow you to make better measurements of the position of the mirror than what an ordinary laser, unsqueezed laser would allow. So in fact, we sometimes are limited by the uncertainty principle, and we've got tricks to beat it.
So I'll take up the next one. That's related to, could you elaborate about the 1875 reunion where the new conditions of a meter were established?
Yes.
The country that hosts that meeting and some of the countries that participated in such a reunion.
Okay, well, I don't remember all the countries. There were, I think, fewer than 20. It was, okay, I'm guessing that it was hosted by France, because part of the treaty was to create an international territory within France. And that international territory is the International Bureau of Weights and Measures, the BIPM. And the BIPM is the place where the kilogram and the meter are still kept. And it was established to house, first of all, to create, and then to house the new kilogram and the new meter. And it's a wonderful place. I urge you to visit it. If you're visiting Paris, it's just outside of Paris in the town of Sèvres. And so among the countries that were the original signers of the Convention of the Meter were France, of course, the United Kingdom, and it may surprise many people, the United States was one of the original signatories of the Convention of the Meter, which means that we agreed by international treaty to make our measurements based on the metric system. Now, of course, the United States is famously one of the last countries that doesn't use the metric system in its daily measurements, but we have legally been metric since at least 1875, and the fact is that we were already maintaining our standards of measurements before 1875 using the metric system. So the United States has legally been metric since the middle of the 19th century, and we have yet to convert in our daily lives to the metric system. Now, why was it necessary to do this? Well, the reason was that the metric system had been adopted officially by France and a few other countries recognizing the advantages of the metric system. Perhaps one of the biggest advantages at that time was the division by 10. The fact that everything was powers of 10 made things much easier, because the traditional measurements were, you know, the foot was divided into 12 inches and the inch was divided in a binary way into half inches and quarter inches and eighth inches. That was really inconvenient for modern technology. So a lot of people were attracted by the decimal way of doing things. And as more and more countries started to adopt the metric system, it became clear that we needed an international way of dealing with this thing. And so the International Treaty of the Meter was signed by a little bit fewer than 20 countries, and now there are 60 full signatories of the Convention of the Meter, and a number of other people who are parties to it but are not full signatories. You see, in order to be a full signatory, you have to pay money, and the money goes to support the International Bureau of Weights and Measures. Somebody has to support all these scientists that are maintaining all these standards and doing international comparisons. So from time to time, people bring their standards to Paris to have it compared. And this is still going to happen because people are going to measure their kilograms using their watt balances, and then they want to make sure their watt balances are doing the right thing. And so they'll take their kilograms to Paris, and other people will bring their kilograms that have been calibrated using their watt balances, and everybody will compare these things. So the BIPM is not going to go out of business. And the signers of the International Treaty of the Meter support the BIPM, among other things. So I hope that answers the question.
Sure.
There was a number of points to that question, so I hope I got to all of them.
Definitely, sir. The other two, I am clubbing them. They are related to, a second is defined as the duration of 9192631770 periods of radiation corresponding to the transition between the two hyperfine levels of the cesium-135 atom. Why this specific number in particular? That is part A. And the other part is, are clocks accurate enough to measure times on the scale of 10 to the power minus 9 seconds?
Yeah, okay. So first, why? Well, the original definition of the second is exactly what you would guess it was. It was 1 over 60 times 60 times 24 of a day. But what is a day? So as the Earth goes around the sun, if you look at the solar day, that changes. So the definition was the mean solar day. Well, how do you take the average? Well, that was never defined. It was left to the astronomers to come up with what they thought the mean solar day was. Now there's another problem. The rotation rate of the Earth is not constant. The tides represent a friction on the Earth that slows down the rotation of the Earth. Earthquakes represent often a redistribution of mass, which changes the moment of inertia of the Earth. And so when ocean currents change, this changes the angular momentum of the Earth, which has to stay constant. So that means the rotation stays, changes. Of course, it's not constant because of the tides, because it's not an isolated system, because there's the moon. So we have all these things that mean that traditional definition of the second is not constant. So just as in the case of the kilogram not being constant because it gets dirty or it loses some surface layers or something, the second is not constant. But it is because that's the definition of the second. So that's intolerable. So they had to change the definition of the second. So in 1960, they changed the definition of the second to be a certain fraction of the year 1900. Now, my thought was, what were they thinking? What a crazy definition to make it a fraction of a year that is half a century ago. Of course, it's constant, and astronomers can do a very good job of extrapolating back to the year 1900, but it just is not the convenient definition that you want. And people have had atomic clocks for already 5 years. NPL in England had installed an atomic clock in about 1955. And the first atomic clock was demonstrated at NIST in 1949. Of course, then it was called the National Bureau of Standards. So we already had the concept of an atomic clock, but they didn't use it because I guess they were just too conservative. But by 1967, it became clear that atomic clocks were so much better than what they could do with astronomy that they had to change the definition. And I guess part of the question is, why cesium? Why not something else? And the answer is that there's lots of reasons. One was that the frequency was really convenient. The 9.2 gigahertz is in what's called X-band. And X-band is a very common microwave standard, and people knew how to make X-band microwaves, how to measure them. It was really convenient because it's been used for radar. So that was one reason. You want the frequency to be as high as you can, because if there are things like magnetic fields that shift the frequency by a certain amount, then it'll be a smaller fraction if the frequency is higher. And cesium has the highest hyperfine frequency of any non-radioactive alkali. So, and you know, the next one is francium, and it only has a lifetime of a few minutes, so you can't use francium very nicely. You have to do it on a reactor, or not a reactor, an accelerator. So francium is not a good choice. So cesium is the best choice for the highest frequency. Cesium has a really high vapor pressure at fairly low temperature. So you don't have to heat the cesium up much beyond room temperature in order to get lots of cesium vapor. So that means that, for one thing, it's easy. And for another thing, it means that the cesium atoms aren't moving very fast. And that's good for two reasons. One is that when they're moving fast, they have a Doppler shift. And you don't want that Doppler shift to get in the way. Well, there's also a relativistic time dilation. So Einstein taught us about the fact that moving clocks run slow because of the time dilation, and that's less. It's also true that in the laboratory, you only have a certain amount of time to make the measurement. If the atoms are moving fast, then there's less time to measure. This is a manifestation of the uncertainty principle. The uncertainty principle for energy and time. You see, if you've got a longer time, that means you've got a bigger uncertainty in the time. You can have a smaller uncertainty in the energy, and that's what you want. But if the atoms are moving fast, then you're going to have a shorter time, which means a lower uncertainty in the time, which you don't care about, and you're going to have a bigger uncertainty in the frequency or the energy, which you do care about. So that's why you want it to be a lower temperature, and that's also why you want it to have a higher mass. So cesium is the heaviest of the alkalis, and that means that at a given temperature, it's moving slower because it's heavier. Another reason, see, there's all these reasons why cesium is good. Another reason is that when you detect the cesium, it has a very efficient detection mechanism called surface ionization. It's got the lowest ionization potential of any of the alkalis. And as a result, when a cesium atom comes close to a surface like tungsten, the tungsten will suck the electron off of the cesium atom. And then with an electric field, you can pull the ion away and measure it. And it's a very sensitive way of measuring. Today, we don't care because we have lasers, and we shine lasers on the cesium atom. But for all these, and so modern cesium clocks use lasers to detect the cesium atoms. But those were all the reasons why, there were more reasons why people chose cesium. And it turned out that when laser cooling came along, cesium was one of the easiest things to laser cool. So it was really good for that as well. We can laser cool cesium down to below 1 microkelvin. And so the velocity of the cesium atoms is less than 1 centimeter per second. And so this makes the atomic fountains really great. The only thing that's bad about cesium, which of course the old metrologists couldn't have known about, is that at low temperatures, it has a big collisional shift. So some people use rubidium instead. So that's all the reasons why cesium was chosen. Now I forget the second part of the question.
No problem, sir. I'll take up the next one in that case.
Remind me of the second part of this question so I can answer that. There were two parts to the question, and I think I only answered the first part about cesium.
Yeah, sure. So yeah. So let me see. I have to just scroll it.
Yeah. Oh, I'm sorry. I should have.
No problem.
I should have remembered better.
So instead of cesium, which other option do
Ah,
you think that is possible that you have already taken
yeah,
care of? Yeah.
well, we've had this panoply of candidates for optical frequency standards. So
Yeah.
for example, my former colleague Subadib is working on ytterbium ions. My colleague in Boulder is working on strontium. Other people are working on neutral ytterbium. Uh, uh, Other people are working on mercury ions. So it's not obvious. Each of these choices has their own advantages and disadvantages. Um, I think we're going to have to work with them for a while, see which of them are most convenient, uh, and it'll take a while before we decide. If I had to guess, I would guess strontium, but we'll see.
Okay. Okay. So I'll take up the next one. Will the eddy current set up due to the electromagnetic field in the balance cause any issues in the measurement process?
Yeah. So if there are changes in the magnetic field during the process of doing the experiment, then that's something you have to worry about. But if, for example, there's some constant distortion of the magnetic field, that will be taken care of. So uh, the current version at NIST is done with a superconducting magnet. So as a result, there's very little extra influence because of, there's shielding due to the superconducting magnet, and there are magnetic shields in any case. And so anyway, there's a lot of things that are done to avoid the possibility that there's magnetic noise. So it's really magnetic noise rather than uh, additional stray fields that cause the problem. So we have, I mean, it's certainly something that we have to worry about. So we do our best.
Okay. Okay. Then the next one is related to Kibble balance, how it's been tough to implement the new definition of SI units, especially unit of mass through Kibble balance or silicon sphere for most of the National Metrology Institute across the globe. And the second part is, can you give some light on the concise value addition on the national prototype of mass?
Yeah. Okay. So the way in which mass is realized and disseminated is basically going to be the same as it always has. The difference is that we don't have to worry about these drifts anymore. So it used to be that everybody would bring their mass standard to Paris and compare it against the Paris standards, and the international prototype of the kilogram would only be brought out every few decades. And between those times, it was drifting, and some people tried to guess how it would drift. And sometimes they guessed wrong and caused all kinds of problems. Now we don't have to do this. A lot of people are going to have Kibble balances in different places, and we can recalibrate the, the, the working kilograms against them anytime we want. And we know the Kibble balance is stable. It doesn't have these problems. So, but we're still going to be using platinum kilograms for comparing between standards laboratories, and then we're still going to be using stainless steel masses that have been calibrated against the platinum masses for sort of things that are done in the field. So all that's going to be done in the way that's already been developed. The difference is it'll be stable forever. We don't have to worry about this drift that's been going on. Another change that's going to happen is that we're going to do better at small masses. Because today, when we want to measure really small masses, uh, the uh, the accuracy of measuring small masses is seriously reduced compared to the accuracy of measuring a kilogram, because in the old definition, the standard of mass was the kilogram. So the easiest thing to do was to compare 1 kilogram to another kilogram. But now, if you wanted to compare a gram, how do you do that? Well, I mean, it's not exactly like this, but imagine I've made 10 100-gram weights. Okay, then I compare those against the kilogram, and then I make 10 10-gram weights, and I compare them against a 100-gram weight. And then I make 10 1-gram weights and I compare them against the 10-gram weight. See, each time I do this, I introduce extra error. Well, with the Kibble balance, you don't have to do that. It works for any size mass that you want. So, so we should be able to measure small masses better than we've been able to do before. So let's see. I'm not sure if I've answered the whole question, but
Sure, no problem. Just let me just okay. So I'll take up there because that is scrolled down. I'll take up that one again after I'll figure it out. So the next one is related to how is the luminous intensity is defined, and
yeah.
is there any new change in the year 2019?
Yeah, so there's not been any change in the candela, and I'm sure that the questioner noticed that I didn't say anything about the candela, and part of the reason for that is that that it's not really a constant of nature. The definition of luminous intensity is just a way of saying how bright something looks to people. And so, in one sense, you might like it because it's the most human of the of of the base units, but it also is not at all a fundamental constant. So basically, it's this: the candela says the constant that is used to define the candela is the ratio between a lumen and the illumination of with a certain color light with a certain amount of power. So the idea is that that defines what we mean by brightness, and the idea is that if a person thinks that something else is as bright as that definition, then that something else also corresponds to a lumen. And it's kind of crazy because people are going to see light differently, and but we need a way of saying how bright light bulbs are. And even though people may see them differently, they don't see them that differently. So the idea of having a lumen defined is not ridiculous. It's just a little bit odd that it's one of the base units. So metrologists often don't like to talk about the candela because it doesn't really fit into the spirit of all of the other units.
Okay,
But
so
there's been no change.
there's been no
It's the
change.
same as it
It's the
always
same.
was. Yeah.
Okay, fine. So the next one is related to the measurement of seconds. And the question is that the meter and kilogram definitions involve time directly. Would this mean that if we construct 1 kilogram on Earth using watt balance and 1 kilogram on the moon, they may differ slightly?
Yes, unless you pay attention. So, okay, so what I think the questioner is pointing out is that time runs differently depending upon where you are in the gravitational potential. So in Einstein's theory of general relativity, he shows that there is what's sometimes called a gravitational redshift. The deeper you are in a gravitational potential, the slower the clock runs. And this has been demonstrated any number of times, and it can easily be seen with the kind of atomic clocks that we have today. So if you build a cesium clock on Earth and use it to run your Kibble balance to measure the velocity, for example, you need a clock to do that, because you need a clock both for the meter and for the timing. And then you do it on the moon, it's going to be different because you're in a very different gravitational potential. Now, from a practical point of view, it probably doesn't make any difference. I have to do the calculation in my head, but the near the surface of the Earth, the effect is a part in 10 to the 16 per meter. So the moon is what, 250,000. Well, that's miles. It's probably in meters. Let's say in round numbers, it's 500,000 kilometers. It's probably a little bit less than that. But if it was 1,000,000 kilometers, that would still only be a shift of a part in 10 to the 10. And we can only measure masses to a part in 10 to the 8th. So it's not going to matter. So that's one thing. The other thing is, and I hope I did that calculation correctly, you know, when you're trying to do things in your head, sometimes you make mistakes. So I apologize if I got that wrong. But time is defined for a clock at the position of mean sea level on the Earth. So if you're careful, you will make that correction and you won't get a different mass, because if you follow what the definition for time is, the definition includes where the clock is. Now, the problem is that as the definitions of time become better and better, like with optical clocks, then figuring out what your definition of mean sea level is becomes more difficult. Especially with global warming, the sea level is rising. And I'm not sure how the redistribution of mass from the polar ice caps into a uniform distribution around the Earth, I don't know what that does to the gravitational potential. I mean, I'm sure people can figure it out, but it's one of those things that we now have to worry about. So it's not clear that making that correction is very good. There's another point. Making the correction to mean sea level sounds like a good idea if you're making measurements on the Earth, but if you're comparing to some clock that is cosmological, like say millisecond pulsar, then the fact that the gravitational potential on the Earth changes as the Earth, and as the planets go around the sun, that changes the gravitational potential on the Earth. Now, we can ignore that if we stay on the Earth, but if we now compare it to cosmological clocks, we have to take that into consideration. And so people who measure pulsars have to correct to the center of mass of the solar system. So this is a problem, and it's becoming more of a problem as we make our time measurements better and better, but I don't think it's a problem for the kilogram.
Okay, okay. So the next one is, what are the maximum limits of reaching the accuracy in any measurement? And is it up to the limit of Planck's constant?
Well, okay. So the limit of every measurement is always noise. And that noise might be quantum noise, or it might be what we call technical noise or classical noise. It's very difficult to get to a place in a measurement where you're limited only by quantum noise. And only then are you limited by the uncertainty principle, when you're at the limit of quantum noise. And I assume that's what the question meant about being limited by Planck's constant, because of course it's Planck's constant that sets the scale for how big the quantum noise is. But there are very few measurements where quantum noise is the key thing. The fact is that the realization of the second is in fact limited by quantum noise. And the reason is that everything else has been done so well, and you end up being limited by how well you can measure how many cesium atoms have changed their state. And you have 1,000,000 cesium atoms, and you have a square root of n quantum noise, and that ends up being one of the, well, perhaps it's not the most important source of uncertainty, but it is an important source of uncertainty in the measurement of the second using a cesium clock. There are others. For example, you have to worry about collisions between the cesium atoms. Remember, I told you that the collisions were a big problem. So that is one of the limitations in current cesium clocks, is the collisions. But what's called the quantum projection noise, that is an important feature. But there aren't very many other measurements where quantum noise is the limiting factor. But we're getting better all the time, and so that means more and more we're going to get things where where the quantum noise is the important thing.
Okay, so I'll take up the last two questions, and then there are several requests from the attendees if you can show those cartoons that which you had skipped.
Okay.
so so
We'll
I'll
do
take
that.
up the last two questions. Yeah, I'll take up the last two questions. The first one is it possible to run the optical clocks continuously?
Yeah.
Uh,
So that's an important question, and so the 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 questioner is obviously someone who's quite sophisticated, because in order to really count as a clock, you have to run the thing continuously. And if you don't run it continuously, then we say it's just a frequency standard. It's not really a clock. And in order to provide the world with a time standard, you really have to have something that runs continuously. And so what happens today is we have a number of clocks that run continuously, and then we have other clocks that run occasionally that sort of calibrate whether those clocks that run continuously are ticking at the right rate. So we have a large number of clocks, and if some of them stop working, well, it doesn't really matter because we have such a large number of clocks, and they're being averaged together by the International Bureau of Time at BIPM. And some of these clocks are commercial cesium clocks, and they're not very good in their accuracy, but they keep things going continuously. But then we have fountain clocks like we have at NPL India, as well as NPL UK, that tell you whether those clocks are ticking at the right rate. So the combination of the two things helps you to keep a good time standard. Now, what about optical frequency standards? They're not yet working for really long periods of time, but they are working for decent periods of time. And so this is getting better all the time. But it's one of the things that's going to have to happen before we make the change of the definition, is that we're going to have these optical frequency standards running for a really long time.
okay, so I'll take up the last question now. How much is the amount of measurement uncertainty requirements for the Boltzmann constant for successful redefinition of Kelvin in terms of Boltzmann constant?
Yeah. Okay, well, so in the old system, where the Kelvin was a fraction of the thermodynamic temperature of the triple point of water, the way in which a good absolute temperature scale was established was using an ideal gas thermometer. Okay, so you have a cell that has helium in it at a relatively low pressure, because helium is nearly an ideal gas, and it works pretty well. And what you end up with is a measurement of the universal gas constant. Now, the ratio between the universal gas constant and the Boltzmann constant is the Avogadro number, right? And that's been defined. So that means that measuring the universal gas constant is absolutely equivalent to measuring Boltzmann's constant. So the whole physical process of defining the temperature scale using Boltzmann's constant is going to be unchanged, because before it was done using an ideal gas thermometer. Now, what we're hoping is that in the future, we will have other ways of measuring it. Like, for example, have a gas and measure the velocity distribution of the atoms in the gas using laser Doppler velocimetry. It's not quite good enough yet to compete with the more classic ways of doing things, but because of the new definition, it will be a perfectly good way of defining the Kelvin in the future if we solve a bunch of technical problems. So I hope that answers the question.
So now that was the last request. If you can show those cartoons,
Yes,
then I'll ask Professor Ghatak, and Professor Anurag Sharma has also joined. He's the president of the Optical Society of India. Then they can give some concluding remarks.
Okay, so here's the cartoon. So remember, what I was saying was that the fact that in the 21st century, the unit of mass is an artifact that was made in the 19th century based on an object that was made in the 18th century is a scandal, such a big scandal that it's made fun of in cartoons. So let me go to full screen so you can see this. So the background here is that this, what you're looking at is a schoolhouse, and inside the schoolhouse, a little girl is asking her science teacher, am I right that we've redefined the meter as the distance traveled by light in a certain fraction of a second? And the science teacher says, yes, that's because the previous definition based on global distances was inaccurate. And we've seen exactly how that worked out. According to the old definition of the meter as being 1/10,000,000th of the Paris meridian. And then she asks, and we've similarly redefined the second, which had been an approximation of 1 over the fraction of the solar day, the one that we've already discussed. And he says, yes, now this is based on oscillations of the cesium atom. So all these things have come up in our discussion now. And then she says, why haven't we changed the definition of the kilogram? This was written before the kilogram definition was changed. And he says, we haven't. And she says, no, the official definition is still the mass of the international prototype of the kilogram, an actual lump of stuff that is stored somewhere. And he says, that's so unscientific. And she says, exactly. What if somebody sneaked in and shaved off a piece? And he says, he's so upset, he says he needs to lie down. And the girl says, I told you there were ways of getting to him. So she's just trying to bother her science teacher with but the fact that this appeared in a comic strip in the US, I find quite remarkable. As long as we're talking about it, let me show you my kilogram. I actually have it right here. This is my copy of the kilogram. Now, it's not a real kilogram. This is a replica that's made out of brass and then coated with something to make it look like platinum. But I wanted to show it to you because it gives you a feeling for just how big a kilogram of platinum is. And you see, I've put on a white glove to handle it to emphasize the idea that if I were to leave a fingerprint on here, you would all lose weight. And that is one of the key reasons why we had to change the definition of the kilogram, because we can't have that kind of thing going on.
Yeah, thank you. Thank you very much, sir. And now may I request Professor Anurag Sharma, Dr. Aswal, Professor Ghatak to kindly switch on their cameras. Yeah. Sir, Professor Anurag Sharma, I think you have to unmute.
Okay.
you. Yeah, fine.
Yeah. All right. So, good afternoon, good evening, good morning, depending on where you are. And I'm really wonderful lecture that we had. We have been interacting with NPL scientists off and on, and we understand the sort of importance of this standards. But this lecture was amazing and gave so much insight into the how things have changed. As an optical scientist, it's only heartening to see that more and more optics is getting into all this business, more lasers, more spectroscopy and things like that. And so it's really, really wonderful, and how the everything is now defined in terms of universal constants. So it's really amazing. So it's an amazing lecture, and I thank the speaker with my bottom heart. A really wonderful lecture. Thank you.
Well, thank you very much. It was a pleasure to join you.
So I request Dr. Aswal and then finally Professor Ghatak.
Thank you, Professor Williams, for giving such a wonderful talk. And on May 20, 2019, we also got revised SI units implemented in India. And what we did is that we have shown the 1 kilogram, the artifacts, as well as our 1 gram Kibble balance. And then we wrote letter to across the country to all the government departments. And in India, the weights and measures are looked after by the Ministry of Consumer Affairs. And then the minister called me and then he said that, how does it matter to a common public? And he said that we are ready to pay you the entire funds for erecting the 1 kilogram of Kibble balance if you show us how it is going to benefit the people. Then I gave them many of the example, say for example, the pharmaceutical industry, where the masses are very tiny, of the order of micrograms. I told that if the uncertainty is large and in case the drug molecule mass becomes double, it will become overdose. And if it is less, it can become underdose and the medicine not work. Or other case, it may give you a kind of allergy. And yes, he said, yeah, this happens, in generic medicines. And then what we said is that in India, those branded company, those who take their measurement calibration from National Physical Laboratory, their quality of the product is very, very good. And then I gave them many, many examples. And finally, they got convinced, yes, the measurements are indeed very, very important. Regarding time, the Indian Standard Time, which we get calibrated with respect to the BIPM, and fortunately we got the uncertainty of 2.8 nanosecond now, and in turn which we give it to our space department, and that has got a great advantage for our NAVIC system. So thank you very much for such a wonderful lecture, and it is not only important from the scientific point of view, it also depends upon the national growth and the harmonization of measurement. If everybody has got a uniform measurement across the country, then the two different parts made by two different people can combine together and can make the entire system without any fault. And that leads to the quality control as well as the quality assurance. And particularly in India, where we have got a large number of MSMEs, and we do feel that the quality of the products that do not come very so well. So our efforts are that everywhere the measurements are unified. And as per our own statement, our estimate, we have got more than 400,000 testing and calibration laboratories. And all of them, they need to have the uniform measurement. And NPL will be celebrating its 75th Foundation Day on 4th January 2021. And for that, I myself edited one book, and that is published by Springer Nature, and the title is Metrology for Inclusive Growth of India. And in that book, that is now known as the ASWAL model, where the government, the policy maker, the industry, and the academia, they all need to get together, and they need to be harmonized. And the only way they can go on equal foot is the accurate and precise measurement, which are traceable to the SI unit. And the Honorable Prime Minister has agreed to grace the occasion, and he is going to dedicate the Indian Standard Time, which we have created, and it's disseminated to ISRO and many other sectors for railway, the power grid, the banking sector, the strategic sector, as well as the environment standard laboratory, where all the pollution measuring equipment will be calibrated with respect to the NPL India. And finally, the certified reference material, which we have already launched 100 in numbers. So we are doing our effort to the best possible way that the measurements, the benefit of the measurements are, the country gets benefited out of it. So thank you. And once again, thank you for such a wonderful talk. Thank you very much. Namaskar.
It's a pleasure.
Thank you, sir. Now, may I request Professor Joy Cutter to kindly give some concluding remarks.
Thank you, Manoj. It was really a wonderful lecture, as has been mentioned by Dr. Anurag Sharma and Dr. Aswal. And it has been for me a great learning experience. And I would like to request Dr. Manoj Saxena that he should put in an effort to have the whole thing as a part of the BSc honors or BSc syllabus. It is very necessary that we require the Hall coefficient and the other things and the speed of light and the evolution of the of the standards and how they have evolved. Everyone should. I did not know quite a few things that I learned today. So, Dr. Phillips, for me, it has been a tremendous learning experience. Thank you so much for your time, for the patience, and we would like to have maybe Dr. Aswal's book should be of help in creating the standards. And most of you would know, I'm talking to the participants now, those of you who had come late, my previous speaker was Dr. Aswal is the director of National Physical Laboratory, which keeps those standards. So maybe they can have show the students how the standards are kept and things like that. I had once been to Dr. Amitabh Sen Gupta's lab, and there I had learned a little bit about it. So for all of us, it has been a great learning experience. If you have any document that you have prepared, if you can share with Dr. Saxena, that will be really very nice. And finally, I must thank Dr. Saxena for his untiring efforts in organizing such brilliant lectures. Thank you, Manoj. Thank you very much.
Thank you very much, sir. Thank you. So any concluding remarks from Professor Phillips, then I'll close the session.
Well, it's been a pleasure to join you, and I was really pleased with all the questions. Excellent questions, and really helped to clarify a number of points that I didn't cover in my talk. And so I'm very grateful to all the members of the audience who posed the questions, and to all of you for organizing this lovely event.
Thank you very much.
One
sir.
final comment, Manoj.
Yes, sir.
Maybe this would not have been possible without COVID.
I was about to say this only.
This would not have been possible without
absolutely,
COVID.
Absolutely.
Everything has its own positive thing. So it's a remarkable thing that you have been organizing these great webinars, particularly today's one, and many students have, and it's a gift of COVID.
Exactly. It's an offshoot. It's an offshoot, and that's why I was about to say the same thing, that we could get Professor William to speak for us, to all the attendees, not only for the 45 minutes talk, but he took up all the questions, and nearly, I'm now seeing the time, it's about 45 minutes additional time for the Q&A. So usually it's the same time which we have spent for the session as well as for the Q&A. And I would like to thank Professor Phillips from core of my heart, and from behalf of all the attendees, the NASI Delhi chapter and the host institution, the Dayal Upadhyaya College, I would like to thank you. I would like to thank all the panelists, Professor Ghatak, Dr. Aswal, Professor Anurag Sharma, and my co-host, Dr. Geetika, for sparing these 90 minutes. And they have been a game changer, I'll say, in our approach towards the standards and how we should look towards the education, imparting education right from the undergrad to the postgrad level. And it's a very well taken point that we should try to introduce these instrumentation, measurement, and times and standards, these topics in the school education, as well as when we are talking about the national education policy. So it will be a very good effort if we can, from the NASI Delhi chapter, along with the help with Dr. Aswal, we can come up with some good brief for the UGC as well as for the NCRT, maybe the CBSC, and we can give them a draft. And maybe if Professor Phillips can help us in finalizing that particular draft, that will be so nice.
That's a brilliant idea. That's a brilliant idea.
Because we have to frame the national education policy for 2020, and that is going to be implemented next year, that is in 2021. So it will be of great help if Dr. Aswal and Professor Phillips can help us in that regard. Okay.
Thank you.
Okay. Thank you. Thank you very much.